general, this is the second track. So the first talk in this session is by Arman Kolozyan from Max Planck Institute for Security and Privacy. And the title of his talk is Language Agnostic Detection of Computation Constraint Inconsistencies in ZKP Programs for via value inference. Sorry if I didn't say it perfect. Thank you all. So please feel free to start, Arman.
So thank you very much, everyone, for coming. My name is Arman. I am currently an intern or a pre-doc at Max Planck Institute for Security and Privacy. But today I would like to present the research I did as part of my master's thesis, which focused on the application side of zero-knowledge proofs, or more specifically, finding vulnerabilities in such applications. And by application, I mean, for example, the self app, which lets you prove attributes about yourself without revealing any additional information. So for example, you simply scan your ID on your phone, and then it processes it and creates a proof that you are over 18 without revealing any sensitive information. Luckily, thanks to recent advancements in zero-knowledge proofs, these ZKP applications are no longer limited to such fixed use cases, as developers can now program their own custom ZKP application. And how does it then work? Of course, you first have an ID where you want to exploit the zero-knowledge aspect of zero-knowledge proofs or the succinctness aspect. And then you write a ZKP program. I'm saying a ZKP program and not just a program, because you have to write it down in a ZKP-specific language, and that comes with its own syntax. For example, we don't talk about functions, but about templates, not about variables, but about signals, etc. And then from this program, code is generated for the prover that will use its part of the code to create a proof. And then code is also generated for the verifier that will use its part of the code to check the proof and then accept or reject it. And by checking the proof, I mean that the verifier has checked whether this proof corresponds to a correct execution of the program. So what might happen in our threat model is that an attacker might take control, and so a malicious prover could generate an invalid proof or a fake proof. And then, of course, the verifier has to reject that proof. However, what might happen is that there could be a bug in the program, and then the verifier might end up accepting the invalid proof. And since zero-knowledge proofs are used a lot in blockchain context, such tiny vulnerabilities can have very severe consequences that can allow the attacker to create fake coins or even lead to the loss of millions of dollars. And this brings us to our contributions, because what we first did is formalizing, like, what is this zero-knowledge proof program? What is this prover side, this verifier side? When is a program correct? Or more importantly, when is it not correct? And in this way, we formalized the vulnerabilities that can occur in this context. Then we turned this formalization into an algorithm for efficiently detecting those vulnerabilities we have formalized. Next, when it was time to finally implement the algorithm, we faced an important question of, like, are we going to support multiple zero-knowledge proof languages or just a single? Like, is there even a need to support multiple languages? And if there is a need, how are we going to achieve this multi-language support? And finally, as part of our evaluation, we discovered some real-world vulnerabilities that I would also like to briefly talk about at the end. But to understand the first contribution of our work, which is the formalization, we have to take a deeper look. We have to get a bit more background, like, on how these zero-knowledge proof programs work. Because if we go back to where we left off, I mentioned that from the code that you write, code is generated for the prover and the verifier. But actually, I lied there, because what happens in reality is that the developer has to write down what is the prover expected to do, an honest prover, and how is the verifier going to check whether that step of the program was done correctly. So the developer has to actually manually write down the code for the prover for generating a proof and the code for the verifier. So here, if we split the two cases, we have code where we want to multiply A and B and assign it to the output. So we multiply the inputs. The developer has to also write down how is the verifier going to check whether this multiplication was done correctly. Well, it just has to check whether A times B is equal to the output. So the prover might then go on and create a proof, which on a very high level is like an association of the variables or the signals in the program and the values. So in this case, the prover passed us inputs 4 and 2 and got us output 8. At least that's what the prover is claiming to have done. And now the verifier will check, okay, do these values actually come from a correct execution of the program, or are these just invalid fake values? So in this case, the verifier will check, is 4 times 2 equal to 8? And that's the case here, so the verifier is happy. So this is more or less how the whole pipeline works of zero-knowledge proof applications on this level, like the programming model. But now you might wonder, yeah, but can't you just, it seems like super easy. You just copy the line and you just change the assignment by an equality check. So why should this ever go wrong? So the question is, can you always do that? Like copy the line of the prover and just change it by an equality? And for that, we have to go ahead and take a deeper look at the allowed operations in zero-knowledge proofs, at least in zero-knowledge proof programming, because it turns out that the prover, the developer, when writing down the code for the prover, it can use addition, multiplication, equality checks, but much more, like division, check whether one number is less than the other, etc. But for the verifier, the developer is only allowed to use addition, multiplication, and equality. And it's more or less because the cryptographic layer at the backend, which we don't care too much about, has put restrictions on us on what the verifier can use in order for the verification to make it quick, etc. And it turns out the fact that the prover can do much more causes a lot of complexities in ZKP programming. Because if we go back and let's look at a case where the prover is supposed to do a division, so it takes two inputs and just divides them. So that's the prover side, and it might, for example, pass inputs 4 and 2 to the program, and it divides 4 and 2, and it ends up with an output 2. But now, how is the verifier going to check whether this step of the program was done correctly or not if it can only use addition, multiplication, and equality checks? So you see, it gets a bit tricky here. And the initial idea of the developer might be, well, let's just multiply out by out and B and check whether that's equal to A. Because if that's the case, then the division most likely was done correctly. So in this case, having received this proof on a high level, this association of variables and values, the verifier will check whether 2 times 2 is equal to 4, and that is the case here, so the verifier is happy, and everything seems to be going fine. But the question is, what if we want to divide by 0? What will happen in that case? So the prover passes us inputs, something for A and 0 for B, and what will happen is we will get a division by 0 error, so the prover will not be able to generate the proof, because the program will crash, it will give this error. But now we are making the assumption that we have an honest prover. What might happen is that, of course, an attacker might again take control and just create its own invalid proof, its own fake proof, where it says, oh, when I divided 0 by 0, I got 5. And of course, this is not possible because, first of all, the program would crash, and 0 dividing by 0, that's not 5. But and that's the whole point of these constraints, because they have to now check, do these values come from the program or not? But what the verifier will check here is whether 5 times 0 is equal to 0, because that's what we said corresponds to this checking of the division. And that's the case here, so the verifier is happy. So what happened here is that the verifier accepted a proof that it shouldn't have accepted. And the whole reason for this is that what the verifier first had to do is check, is this B not 0? Like have a constraint to check whether B is non-zero before checking whether O times B is equal to A. And these language developers are aware of these issues, so they provide protection mechanisms. One of them is called signal tags, signal variable, and the tags are like attachments you put on the variables to write down a certain assumption you have. So here we put an assumption. We say every time you use this function as a caller or this template, make sure to have already constrained B to be non-zero. And this assumption basically says, I'm not doing the check here. I know that I'm not doing it, but I assume that you will do it when you use the function and as a caller. And the whole reason for this is performance. Because if we would have already done the check, the caller would have already done the check, and we do it now inside the template, because you might wonder, why aren't you doing the check here? Why put it as an assumption? And the whole reason is that if the caller would have already done the check, we would end up doing the check twice. And in zero-knowledge proof context, or in programming in zero-knowledge proofs, we want to, of course, minimize the number of constraints, the number of duplicate constraints, because it has a direct impact on the performance. So hence, we end up with many such assumptions in library templates or in library functions that you can reuse. And these assumptions are sometimes even not documented. So sometimes the developer uses templates that the library provides, but they don't know that they have to first put these constraints before using them. But unfortunately, the compiler does not do any checks. The compiler does not by default verify, did you respect those assumptions? When using these templates, did you put the necessary constraints? And hence we end up with many such bug examples in the wild where assumptions are violated, where this prover side, this computation side, and the constraint side of the verifier do not match. So you see missing check that we have found a lot in reported GitHub issues or in collected GitHub bug trackers. And this then brings us to our contributions. Now we have the necessary background to take a look at our first contribution, where we did the formalization, where we try to understand, okay, and if you violate these assumptions, what are the types of vulnerabilities that can occur, etc. And in the paper, we have given many formal definitions and proofs, but here during the talk, I want to give the intuition by going over an example, over our division by zero example. So here we have the program again, and we will split it into the prover and the verifier side, or the computations and the constraint side. And what our formalization proposes to do is take the set of variables or signals on both sides and look at all the possible set of values and see whether can this be generated by the prover and will this be accepted by the verifier. So you basically check for each set of values, can it be accepted by the, will it be generated by the program and will it be accepted by the verifier. So for example here, 4, 2, 2, 4 divided by 2 is 2, it can be generated by the program and the verifier also accepts it given its constraints. And you keep on doing that, and at some point perhaps you hit towards this set of values that cause a division by zero error or violate any assumptions, but the verifier accepts them, or the other way around. And here we end up then with an inconsistency, and then the developer has to come in and fix the issue to make them match. Now, of course, if you would have put the tag, the assumption, then we say that the program is correct, because in this case, the check is not there, but there is this assumption of like, I know the check is not there, I assume the caller will do it. It becomes problematic when you use this function or template as part of your, as a caller, but you don't put the necessary constraint. Then you again have an inconsistency. And to put this in a correct program, what the developer has to do is first add a check that B is non-zero. Of course, it is very simplified syntax, but it's just to bring over the ID, and then we end up with a correct program where the computations and the constraints match. And by doing this formalization and taking into account the preconditions, the signal tags and post conditions, because the signal tags are like an example of how a precondition could look like, we managed to formalize several vulnerabilities that can occur in this context due to these violations. One of them is division by zero, but another important one is, for example, the arithmetic overflows, where there are assumptions on the range of possible values that the input should have, but as a caller, you don't first put the constraint to make sure the verifier checks for that assumption before calling the template, and that causes also a lot of issues, where you can, for example, end up proving that 1 million is less than 1 because of these arithmetic overflows. So now if we go to our next contribution, because this formalization allowed us to define all of these vulnerabilities, but then the question is, how are you going to put this into a detector? How are you going to implement this? Because if we naively go over all these possible values, we have to iterate over P, the modulo prime P, for each signal. And by default, this modulo is super large. So of course, this is not achievable. This will be super slow. So we had to think about, okay, we still want to make this detection. So how are we going to turn this into an efficient algorithm? So we had to come up with ways to approximate the information we have and use that for bug detection. And how are we doing that? So we go back to where we left off. And our proposal, or the way our algorithm works, is we approximate both sides. On the prover side, we use signal tags. We use the specification to approximate what an honest prover is expected to do. For example, we know that an honest prover is expected to pass non-zero values for B. And if you have the specification, we use that, and that gives us an idea of what an honest prover is expected to do. Or for example, there could be a tag that A is supposed to have a maximum value of 15. So by using these signal tags, it already suffices to get an idea of what a prover is expected to do. Then on the verification side, we approximate this set of values by having like ranges of possible values that this verifier might accept. I will soon explain how we get to these ranges, but instead of going over all possible sets and checking whether the verifier accepts or not, we look at the program and we approximate that the only possible values that, for example, the verifier will accept for B is any value between 0 and 5. We get that information. I will explain how. And by having these approximations of sets of possible values that the verifier will accept, we already can do this bug detection. We can, for example, see that, at some points it might accept a value 0 for B, and since B was supposed to be non-zero, we have vulnerability. So it suffices to approximate the values. Of course, since we are over-approximating, we are sometimes including values that it would never accept. It might be that we flag a bug, while in reality there is no issue, so we might have false positives. But the question is, of course, how do we get to these values? The prover side, we can just get it by taking the specification. For the verifier side, we refer to related work of Shankara et al., where they provided inference rules. And what these inference rules do is, basically they exploit the fact that you have many reoccurring patterns in those zero-knowledge proof constraints. So what these inference rules say is like, if you see this kind of pattern, then you know that you can derive this information about the variables that occur in that pattern. So to give an example, if you see that the verifier checks whether x times x minus 2 is equal to 0, if the verifier is checking for this, then you know that the only possible values that the verifier will ever accept for x is 0 or 2, because otherwise the constraint is not satisfied. And since you are over-approximating, we might even say it accepts values for 0, 1, and 2 for x. And so via this, we of course extended these categories of inference rules that the related work provides, and we also added some extra inference rules in those categories to help us with detecting these issues that we have formalized. So if we go back, on one side we have that we use the specifications for approximation, and for the verifier side we apply these inference rules. And we keep applying them until we reach a fixed point. In the paper, we have provided proofs that the algorithm will eventually terminate, etc., and that these inference rules are sound. But here, I just wanted to bring over the high-level idea. So then, when we went ahead and wanted to implement this algorithm and check how much of these bugs we can flag and detect, the question was: are we going to support multiple languages? Or not, because there are multiple zero-knowledge proof languages out there: Circom, Socrates, Noir, etc. And it seems that many of the tools that are out there, they mainly target Circom. So what we did is we did some sort of empirical study on GitHub, where we looked into, okay, for all these zero-knowledge proof applications that are out there on GitHub, which language are they actually using? Because if they all are using Circom, then it makes sense to only build a tool that targets Circom. And so if we take a look, we have there the years on the x-axis, and then we have the new repositories that came out in that year. And we also see the languages that have been used for those repositories. And we see that, for example, at a certain point, Circom was super popular, and it still is. But the language Noir, for example, is gaining traction. And as we know that these arithmetic overflows, etc., can also occur in Noir, we thought, okay, it makes sense to come up with a language agnostic approach. But the question is, how are we going to achieve that? How do we build a tool that, how do we avoid building a separate tool for each language and build a tool for all these languages at the same time? And while reading the literature, we came across this compiler infrastructure of Alex Ozdemir et al., where they provide a compiler that translates different zero-knowledge proof programs written in different zero-knowledge proof languages, or just cryptographic tools in general, to an intermediate representation, and then to different outputs for different goals. But our the main insight here for us is that it operates over an intermediate representation. So our idea was that, okay, if we can target this intermediate representation with our tool, then we have a language agnostic approach, because all you have to do is translate the program to this intermediate representation and then run our tool on it. And in the meantime, we have also added support for CIRCOM and Noir to this intermediate representation. And via this way, to the best of our knowledge, we were also the first tool that operates over this high-level intermediate representation that has a view over both the computations and the constraints. And actually, the compiler already does this splitting for us, so that work is already handled for us. We already have a view over what the prover is doing and what the verifier is checking. Now, I also want to briefly mention a few things about the evaluation of our tool. What we first did is we evaluated on small programs from a benchmark suite provided by a related work, which is Cyber. It uses formal verification, SMT solvers, to check for bugs or to formally verify the programs. And yeah, the problem with SMT solvers in zero-knowledge proof context, using them in zero-knowledge proof context, is that there are a lot of nonlinear equations in zero-knowledge proof programs or in the constraints, and it seems like these SMT solvers have a hard time to deal with them. Like, the theories are not mature enough yet to handle them. So this verification via SMT solvers cause quite some timeout. So indeed, compared to our tool, which uses these inference rules and this value inference engine algorithm to detect them, we are much faster, like 2 orders of magnitude. But of course, sometimes, since we are approximating, we flag issues like a division by 0 issues, while in reality there is no bug. So there is always this trade-off, or are you going towards a formal verification style or more static analysis where you then approximate and get some false positives. These were some toy examples. We also looked into real-world programs of companies like Microsoft, TikTok, and Self, which is like the app that lets you prove these attributes about yourself without revealing any additional information. And we managed to find vulnerabilities that are covered by our formalization in all of these programs. These programs range from, for example, Microsoft is using zero-knowledge proofs to prove that your mobile driver's license is valid. TikTok is using them in the context of trusted execution environments, etc. And we managed to find many vulnerabilities, and we also went in a call with some of them. They merged all of our pull requests. They accepted our fixes also for these issues. And the main idea behind these issues is often that these assumptions have been violated. For example, you have these arithmetic overflows, which allows then a malicious prover to end up creating an invalid proof that is accepted by the verifier. And actually, the bug we found in the Self app had already, this Self application had already been audited by a major zero-knowledge proof auditing company, and the bug was not detected, so we also received a bug bounty for this issue. So to conclude, we saw that in this talk that zero-knowledge proof programs often violate these assumptions or implicit assumptions. So our solution for that was to detect computation constraint mismatches and to make this formalization tractable. On the one hand, we use the specification to get an approximation of the behavior of the prover, and on the other side, we use these abstract values, these approximated values. And then we also saw that there is a need for language agnostic bug detectors, and our proposal there, or our solution, was to use intermediate representations. Very recently, Veridice, which is another company for auditing zero-knowledge proof programs, they came up with a new intermediate representation that's supposed to be, for example, more readable. So it highlights the significance of this contribution. And for further technical details, I refer to our code and our paper that has been accepted at SMP that I will soon present there. We wrote this paper together with my supervisors at Nokia Bell Labs at the university, also at ZK Security and UCL. So I'm also happy to take any questions that you might have now. Thank you.
Thank you, Arman, for the nice talk. Are there any questions? Yes, go ahead.
Yeah, so you've mentioned Veridize at the end, and I'm not entirely, like I don't exactly know how they proceed, but if I'm correct, they use a technology where they kind of, so here I think you're kind of checking whether there is a mismatch between what the prover and the verifier are doing. And I think Veridize is doing something like they check that what the whole system is trying to do is kind of deterministic. And would actually a similar approach be beneficial to us? Like, do you think that checking determinism would be another way to tackle your issue, or to use like similar approach to make it more efficient or just better in some aspect?
Yeah, so it's a very good question. Indeed, the tools of Veridize, for example, the PICUS tool, it looks only at the constraint side and try to see whether what the verifier is accepting, is it deterministic or not? And it is an important property, because if the constraint side would be non-deterministic, then it means the verifier accepts for the same input 2 different outputs. So I could provide a proof that I'm over 18, but also a proof that I'm under 18, and it would accept both. So if I'm a child, I could provide a fake proof that I'm over 18, and they would accept it. So there is importance in that direction. But with our work, we argue that just by looking at the constraints of what the verifier is doing, you don't have any idea of what an honest prover is expected to do. So if the prover is expected to prove that they are over 18, but the verifier is deterministically perfectly checking whether you are over 17, then if you don't look at the computation side, you never know that what's the honest prover exactly expected to do. So I would say that what Veridize and I would say the deterministic checks is one of the checks you can do, but you also have to check do the constraints match the computation side to allow breaking these assumptions that there are. So yeah, the definition of under constraint is currently in the literature is like it overlaps with the determinism, but we try to come up with a new definition that also takes these mismatches into account. So we have a more general definition of what under constraint means.
So thank you, Arman, for your talk. Let's thank the speaker again. So the next talk is going to be